And very warm welcome to the Oxford Martin School. I'm Ian Golden, the director of the school, and it's a great pleasure to be introducing the second in our seminar series of Ideas into Action. This is a seminar series which celebrates 10 years of research in the school, as it's our 10th birthday, and what we're trying to do in it is highlight some real nuggets of the work that's been going on across a very wide spectrum of research. And I'm delighted today to be able to introduce two colleagues who've been working on energy systems, trying to address the great challenge of climate change by coming up with new ideas for how to create energy, and particularly focusing today on solar. Malcolm McCulloch has been involved in the school for a long time. He was the co-director of our Institute for Carbon and Energy Reduction in Transport. He's an associate professor in the Department of Engineering and head of the Energy and Power Group at Oxford. He's been involved in many, many programs in developing countries as well as advanced. And today he's going to speak about a new program, or an aspect of a new program that we've just launched, which is integrating renewables into the grid and particularly focusing on solar. Professor Henry Snaith has been the co-director of our program on solar energy. He's the head of the Oxford Photovoltaic and Optoelectronic Device Group. He has been absolutely pioneering in his work on perovskites. He's started a whole new area of research in this, and he'll be telling us today about his very exciting discoveries and work on organic photovoltaics. I also want to take this occasion to congratulate Henry, because I don't think I've done it publicly yet, on his becoming a member of the Royal Society and many other things. So Malcolm will go first. He'll speak for about 20 minutes. He'll be followed by Henry for 20 minutes, and then if they stick to time, we'll have about the same amount of time that they've collectively taken for discussion. Malcolm.
Thank you, Ian. The question that I wanted to address this afternoon was to say, can renewable generation technologies power the world, and what are some of the challenges that are going to be associated with it? This talk is going to be a kind of big numbers and approximate variables, but just to kind of get an idea of what some of the scale of the challenges are. So don't hold me to the second decimal place. I'm lucky if the first significant figure is right. So let's take it from there. The problem is that energy, you would have thought, is a well-known and well-defined subject, but even people like BP, who collect the world's traded energy, still has some challenges with their numbers, because the word is they collect their world's traded energy. So if you have a look there, we spend something like just on 13,000 million tons of oil equivalent per annum. That's the total energy we consume. If you look at 7 billion people of us, that means it's effectively the same as all 7 billion of us burning a 2 kilowatt heater 24 hours a day, 365 days a week. So that's quite a lot of energy that we're consuming as a planet. The challenge is that that's the number of traded energy. If you actually include the amount of informal energy use, such as biomass, and particularly in the developing world, you can add another at least 10% on top of that. So the question is, can we actually meet that requirement using renewables? Now, if you look at this graph, we can see that the bottom low one is oil. Okay, the next one up is coal. Then we have orange is nuclear, hydro, renewables is the tiny blue one, and then we've got coal at the top. What's interesting is this is the first year where we've actually used more oil than we have, used more coal than oil, and that kind of tells you what's happening in China. Also, you can see in 2008-9, there's a dip there, so we can see clearly there's a strong correlation between energy use and economic well-being. So we want to make sure that we can continue to prosper, but not maybe send out as much CO2 as we have at the moment. So the question is, can we grow that blue and orange streak up to cover the whole lot, and what will it take to do that? So let's start off with a good news story, which is Henry will talk about in a little bit more detail. It's basically everybody's heard that the cost of solar panels have come down dramatically. And we can see in sort of like 1976, they're over $100 per watt, and that's very expensive. And at the moment, they've come all the way down, so a mere 40 years later, they're looking at something like between 35 and 40 US cents a watt. And that's a huge change in a very short period of time, and Henry will be talking about how we can push that even further. So let's have a look and consider solar, whether that's appropriate to be using. So if you have a look at the total resource, this map clearly shows us that the amount of energy we can actually capture around the world. And if you have a look at the scale that we've got here, is that we say that if you've got a 1 kilowatt panel installed, you can basically get something like 2,500 kilowatt hours of energy per annum out of that panel. And you can see that clearly there are places like here in the middle of Africa, middle of Australia, and places in the US where you can clearly get over 2,000 kilowatt hours per annum. If you look at something like the UK, you can see we're sitting right down in those colors, and actually a typical panel that we run in Oxford, part of the low carbon, West Oxford Community Renewables, we get about 990 kilowatt hours per annum. So the question is, if we assume that we're being optimistic and we said, okay, if we were operating in some of these really great regions there, approximately how much energy would we need? It turns out that if you take our total energy requirements that we have, assume that's converted to electricity so we can ignore the conversion losses because you're producing high-grade energy, we need something like 30 trillion watts or 30 terawatts of energy. And assuming that our installed cost is something on the order of $1 per watt, including some of the back-end systems, that means we need of the order of $30 trillion to just use to produce all our energy requirements. Give that an order of magnitude to give you a feel for it. The global GDP in the world is about $80 trillion. Okay, so that means that we can start to do something. What's also interesting actually is that if you look at the total energy use, it's about 10% of GDP, so we are spending something like $8 trillion per annum on energy anyway. So if you put in something like a 20-year period, we could actually start to take a ever-increasing proportion of that energy spend, convert it to solar, and that could potentially work. So the economics are kind of getting there. Not quite there, but they're getting there. If you have a look at wind, which is the other alternative, okay, the immediate challenge we see is brown is good and blue is bad. And so we can start to see there are actually only a very few areas in the world where there's a significant amount of wind resource. So that's going to be slightly more challenging. Also, what you find is you need a significantly larger area for these wind densities to be able to generate the area. So if you look at to say what is the total land requirement that we have in order to do both solar and wind, and potentially bio as the last one, it's interesting to see that for solar we need something about the size of the UK, or it happens to fit my map a bit better, something the size of Romania. So if you look at that total size there, if we fill that out completely wall-to-wall with solar, I'm assuming that we got an energy density of 2,000 watts, which is not quite true for that particular location, but it gives you an idea of scale. The amount of land we need is about 200,000 square kilometers, which is equivalent to about 4% of the contiguous USA. So contiguous USA is basically all the states excluding Hawaii and Alaska, so basically the main bulk. And that kind of gives you an idea of what we require. If you look at something like the high-end wind area, and we're looking at an average mean wind speed of 8 meters per second or better, basically need something of that size area there, which is equivalent to about 30% of the USA. And if you looked at something like biomass, you need something quite a bit larger in order to represent that. So what I'm going to do is I'm going to want to concentrate on these two here in particular because they're particularly useful to Europe. Biomass, I think, is of particular interest into places like Africa and Southeast Asia. And that's a topic for another day. It is useful to have a look to say, okay, that seems like a huge amount of land mass, but if you compare it to farming, it's actually quite small. Over half of the land's surface is now claimed by farming, and 60% of that is devoted to livestock. So you can see that we're already quite used to doing terraforming. It just happens to be agriculture which is doing it. So to change it to energy is not going to be a huge challenge. One of the nice things is that we looked at the main energy belts is they tend to be away from where the farming is. Although, again, that is something we need to be a little bit careful of as we go forward in specific aspects. The challenge that we have, though, is that the resources we saw, particularly if you look in Europe, occur in different places. So we kind of saw that the wind was really good in this kind of area, the North Sea. Solar is really good down the south. If you want to look at some of the storage capacities, we need to be near mountains. So we've got places around the Alps and also in Norway and Sweden. So in order to make the system actually work, we are going to have to start thinking of how do we actually connect these pieces together so that we can start to share the energy resources around the world. And so therefore, one of the challenges that we're going to have to say is that one of the options is to looking to say, how can we actually start to create a large supergrid where we can start to shunt the energy around from where it's produced to where it's actually needed. The challenge with this, of course, is you can see these little shaded lines here, is that we're crossing borders. And as soon as you cross borders, politics comes into rule. Also, if you have a look here, a lot of it's crossing land masses, and small-scale politics also comes into rule. In other words, things like NIMBYism and the like, where people are saying they don't want these brand new power lines going down their route. In fact, that's one of the reasons why there's supposed to be a big north-south spine going in the UK, and after 5 years it became clear it was going to take another 20 years to get the consent, so they basically took the cable off the sea and they went from North Scotland down the sea, down that side there. So what we can see is that connecting the electricity grid is great, but the politics comes in the way and makes it a lot more challenging to do. If we start to concentrate a little bit in the UK context, it's just a microcosm of what some of the challenges are. I think it'll start to indicate where we might be wanting to move and what some of the issues are. So if we have a look at UK solar, in 2011-12, DEC made a prediction, well, they got some consultants to make a prediction of what like a medium case and a low case scenario would be of take-up of solar if they introduced feed-in tariffs. Just talk to your person next to you. You've got 20 seconds just to say hi and what happens next. What actually happens? Go. Right, so, okay, so just on the side here, just to make sure that, sorry, apologies, Ian just pointed out, these units here are megawatts, so that's basically 10 gigawatts, 9 gigawatts, 8 gigawatts, 7.65. And just to give you a feel for it, the peak load of the UK is about 60 gigawatts. Okay, so that's 10% of the peak capacity. So what happened next? That's what happened. Okay, so you can see that actually, when the market conditions are right, it's amazing what happens. Things can move extremely rapidly. And to me, this is a cause for optimism. But it's also a pause for thought and caution, because it means that we've actually moved a lot faster than we anticipated, and therefore the problems are coming a lot quicker than we originally anticipated. And that's exactly what the issue that we're addressing in our program on how do we actually integrate that amount of solar into the system. Let's have a look and see this graph here. Basically, again, everything's in megawatts, so that's 60 gigawatts sitting over there. This color scheme tells you what the power is. This, on the right-hand side, is the time of day. So we start from midnight through to midday through to midnight again, and this is the day of the year. And you can see at the bottom we're going from 2013 all the way to end of 2014. And this tells you what the load requirements are. And we can see that obviously that in winter we peak, so it's much higher in the winter than it is in the summer. We can see the stripes coming through, those are the weekends, and we can see that's when the sun goes down. So we can see there's a strong lighting component that's required. So we need to match that, and the challenge that we have in the system is that we need to match that on a second-by-second basis. Because of improvements in batteries, I'm going to more consider to say, actually, let's have a consider if we can match at least the daily consumptions, because I think the intraday variations are manageable. Can we measure the intraday and the seasonal requirements? So if we have a look at solar, so this is now sitting at something like, getting solar data is extremely challenging because bizarrely, all the solar farms are below 100 megawatts, therefore the national grid doesn't actually connect them. So this is a panel that I've connected off a small panel in Cornwall, but as a lot of the solar panels are there, it's kind of representative. And you can see there's a definite seasonal trend. And the problem that you have is that in January and winter is exactly the time when the peaks are and where the solar is a minimum. So that's a problem. Also, we can see that actually in today is that we can see at noontime it's pretty good, but in the evenings it's not so great. Anybody remember the summer of 2013 when it was so sunny? That's sitting there, so we can see what happens. So let's have a look and see what happens with wind. Okay, so again, this is megawatts, and this is megawatts installed. Remember, solar is sitting at about 18 gigawatts. We can see now we've got something like 13 gigawatts of wind done, and as anticipated, we'll go up to about 16 gigawatts by the end of next year. That's what's consented. What actually gets built is anybody's guess. But that's kind of what the trajectory we're on it. So if you have a look at what happens in terms of what does the wind look like, and now we can see that we start to have a kind of like a seasonal variation. So we can see within the day, it actually blows at nighttime. Because the problem with the sun, it doesn't operate at night, so it blows during the day. That's great. We can see it's summer. It's very black, so there's almost nothing happening there. And winter, it's quite strong. So what we do is we can see that actually wind actually starts to match some of our profiles quite well. So let's see what we can do to utilize that wind. So in the short term, what I did is to say, okay, let's take the wind that we've got at the moment, okay, which is something like 18 gigawatts, and double that, which I think is really reasonable to do in the next 2 to 5 years. And assume we had a 24 gigawatt base load, which would be some of our conventional systems. What we then do is we get a profile there where the black is the demand requirement and the red is actually what matches. And you can see we're actually starting to match that reasonably well, all looking good. Except if you look in careful detail in this little corner here, you can see that the load is significantly higher than the demand that we're given. It doesn't look like it's very big, but we've got to be careful because that scale there is a terawatt hour a day. Every one of those little bumps, remember I said, was a weekend. So that's basically 3 weeks of work, 3 weeks there where you're losing something like 0.2 terawatt hours, which means that we left out with about 4 terawatt hours of energy is missing in that space. If you're going purely renewable, we've got to somehow replace that with renewables. If we only stuck with solar and wind, it means that we're going to have storage somewhere. 4 terawatt hours of storage is massive, absolutely massive. To give you an idea, the Tesla Powerwall that's coming out is about it's $3,500, and it's going to cost only 10 kilowatts. So we're going to need, every home is going to need about 17 of those in order to match that up. Okay, so that's quite a price tag in order to do that. So storage alone is not going to match it. We've got to look at being slightly smarter than that. So that was basically saying, if we just took a base load, what else could we look at? Well, what we can start to do is actually start to match up, and we can see that the solar data and the wind data are actually antiphasal. So that in the summer, the wind is low, but the sun is high, and those two are there. And what you find is that if you've got something like 5 times the wind renewable, 5 times the installed capacity of wind, and it turns out to be about 70 gigawatts of sun, you can basically start to match the profile that we need relatively easily, and we need about 2 to 3 terawatt hours of storage to balance that absolutely. The advantage is that in reality, we won't be doing it with real storage. We'll actually start to be using peaker plants and the like to actually cope with that until we get the technology costs coming down. I've talked a lot about storage, so what are the costs of storage? Well, when I started working with Ian as part of the Carbon Energy Reduction and Transport Institute, batteries are kind of critical for electric vehicles. So we're looking at batteries, and it's like 3-4 years ago, you're looking around about $1,000 per kilowatt hour of storage. Now remember we said we needed a terawatt hour, so a kilo is 10 to the 3, a tera is 10 to the 12. That's a lot of money sitting there. But what's been interesting is that if you actually look at the prices and what people like Nissan and Tesla were actually doing, and the way they did is they looked at different models of the vehicle, looked at what the difference in the price was and the difference in the energy storage, and worked out what the marginal cost of batteries are. These are these green curves. So we can see they're starting to come down significantly, whereas they're no longer sitting at this like $1,700, actually more realistically like the $300-400. Some of you may have noticed that a little while back, last month, Tesla actually announced the prices on the Powerwall, and that's the price that's actually coming today. It's about $166 per kilowatt hour. So things are starting to come down quite dramatically. Elon Musk is putting quite a big bet on this to actually make it happen, and that's the size of the factory that he's looking at. Now, to give you an idea, Those wind turbines there have a 100-meter blade radius. So you can kind of get a sense of scale of what the size of this plant actually looks like. He started this year. The first batteries are coming offline in 2017 and will be in full production by 2020, by which time it's producing something like 35 gigawatt hours of batteries per annum. Remember we said you need about a terawatt hour? That's about 30 years production of this guy. Okay, so it kind of says the numbers are big, but the technologies are coming along. So quick conclusions. Renewable energy can meet the energy needs, but it doesn't always meet it at the right time, and that's why I use the word power there. It doesn't always deliver the power at the right time. In order to arbitrage that and to balance that, we either need storage, which is what I mean mainly talking about, or transmission, or what we think is a balance of the two. It's technically feasible. We can absolutely do it. The economics we saw, it's actually getting there. You know, if we use something like 20% of our energy budget over the next 10 years, we can actually deliver this. But, and there's a big but, the markets are not in place. They're not there. How do people get compensated for the capital they deployed already? How do we actually get that incentives changing over? And more importantly, the politics are not there. And this is why places like Paris are going to be very interesting at the end of the year. So, to conclude, yes, renewables can do it, but not on their own. We need other things, supporting things like technology, storage, and transmission, but we also need markets and politics to go in the right way. Thank you.
Okay, can you hear me? Is the microphone working? Well, thank you very much. So I'm going to follow on from Malcolm. I'm Henry Snaith, and hopefully I can find my presentation on here. There we go. So I'm going to sort of take a more of a dive into solar technology and try to keep it entertaining. I very much enjoyed Malcolm's presentation. This might get slightly more technical, but it shouldn't get too technical. So I'm not going to dwell too much on whether we think solar energy is a good idea. I think the general consensus is it is. But sort of how much energy is there? Malcolm sort of showed what fraction of the Earth we needed to cover. This is just sort of to put into perspective the scale of the Earth compared to the Sun. That's it. If you brought the Earth up to the same position, it's about that size with respect to the Sun. So this is a massive nuclear reactor. It's ginormous, and it's producing more than enough power for our needs on planet Earth, even though we're 1 astronomical unit away. So on to something a little bit closer to home, let's say, the solar technology, the sort of technical driving block behind making electricity from sunlight. This is a picture of a silicon solar cell, a schematic. It's a drawing. Just to describe to you how the system works, it's made from a wafer. That wafer is either P-type or N-type silicon. That means positive charged or negatively charged. That's to do with electronic doping, for those of you not familiar. And all these other layers basically ensure the charge will flow in one direction. You absorb light in the semiconductor. That gives electrons, negative charge, energy, kinetic energy, to move through the system, and they are connected on one side by an N-doped, a negatively charged region of silicon, on the other side a positively doped region of silicon. And that makes sure as the charge flows out of this top layer and then back in the bottom layer. That generates current. This is the device, and it's been around since 1954, so it's quite old. And this is, I'll just give you an idea of how you make a silicon solar cell. Not that you want to go off and do it, but just to give you an idea of what's in it. It starts from sand, so it is absolutely abundant. There's no problem of abundancy there. But this needs to be basically reduced from silicon dioxide to silicon in a furnace at about 2,000 degrees. I'm not going to go through all the steps, but basically there's a lot of chemical. Some of them are nasty and need to be made sure they're dealt with properly, and a lot of heat and energy. But at the end of the day, you end up with something which is sort of solar-grade polycrystalline silicon. And then this needs to be melted again in a big furnace for a few days at about, I can't remember what temperature, either 2,000 or 4,000 degrees, pretty hot. And that ends up coming out as a big ingot. And then that ingot needs to be sawed up, or at least the ingot needs to be sawed up into a nice square. And then that square needs to be sawed up into fine little wafers. They need polishing, curing. And that wafer there, after all this process, actually this has got so cheap That's about the same price as glass. It's not that expensive. It's about $7 a square meter for these wafers. They then need to be turned into solar cells. So it is a laborious process, and you wouldn't predict it would be cheap. But as Malcolm showed, this is the same data he showed, if you like, on a slightly different plot. The cost per watt peak of silicon PV from 1977 to today has come down by orders of magnitude, and now it's much less expensive for producing power in some places than oil, than producing electricity from oil. So that's a really dramatic difference. It's illustrated really nicely on this curve. This is taken from a Bloomberg report, and I think it's sort of termed the Terradome. I'm not really quite sure why. Someone probably knows. But this is the cost of power from different sources, and this is the cost of electricity from PV. So it's coming precipitously downwards, and it's actually crossed in some places in the world. This is taken from sunny locations, cost the price of producing electricity from these other sources. So this actually causes, the first thing is people are now noticing PV. Even when this was up here, with the trajectory, people wouldn't believe it would get down to here. And it makes a massive difference. The fact that you can actually produce electricity cheaper with PV in some places than gas, for instance, makes a massive difference to people's perception. And there's really been a transition over this last year where it's being sort of generally understood that it's inevitable that PV will be a big part of the future power. So that all sounds good. And one sort of slight, in essence, downside or issue that we might come across is that if you're going to now build a new gas-fired power station with a 30-year sort of lifetime, it's actually quite a risk. All of a sudden, especially with these costs coming down, it suddenly becomes a risk to invest in conventional power. And we might even see, a downside of that is we might see a time when we really have a lean period in terms of power before we really deploy enough renewables, because it's ceasing to be economically viable to install some of these other ones, especially if you look at the projected costs forwards. Just to sort of think into the future more rather than into the past, how do we now, how will solar compete with, let's say, electricity from gas going forward with scale? If we continue the trajectory of growth in sunny locations, this is dollars per kilowatt hour for the price of producing electricity. US cents, 6 cents per kilowatt hour is the price of the cheapest installed electricity. Actually, there's some even been done for 4.5 cents per kilowatt hour. That compares to around 7 cents per kilowatt hour for producing electricity from gas. And with increasing the scale, we expect about a 16% reduction with every doubling of scale. And that would follow the historic trend. And that's the sort of trend you see with technologies. So another thing that's interesting that people are starting to realize is now electricity can be coupled to the price of electricity can be coupled to the advancement with technology rather than more traditional sort of costs of natural resources, which generally go up. So we could see a difference, and even in average sort of mid-Europe, we could see the cost of electricity coming down below that of producing gas. Now, what I'm not addressing here is obviously storage and what do you do with that electricity, and Malcolm gave a nice presentation on that, so I won't. But clearly, for the real penetration of PV to be a sole power supply, which I don't ever think it will be solely PV, but for that we need very, very good and cheap storage as well. So how do we enable this? So the next part of the talk, I'm going to talk about stuff more close to home, and it's related to the work we've been doing in the Martin School. But just before I get there, I'm going to show you this chart here, which is the National Renewable Energy Laboratories chart of the best efficient solar cells in the world for the different technologies. So you can see in this region here, there's been a lot of new technologies spring up. But what I want to draw your eye to is this blue line here that's crystalline silicon. This is the stuff that's basically powering us at the moment. There's another technology here, this green with yellow dots, that's thin film. I'm not going to go on about that. That's also actually producing about 10% of our electricity, PV electricity. And it's these ones up here that are the really efficient ones, where we can get up to 46% efficiency under concentrated sunlight, or under full sunlight, about 37, 38% efficiency. Now, why don't we use that? Basically, because this technology is very expensive. It costs about $10,000 a square meter, and it's because you have to grow these semiconductors via something called epitaxial growth. Basically, atom by atom, you have to grow a crystalline material on top of each other, and it's challenging. But if we could make stuff that was more similar to silicon or some of these other technologies, but get to these sort of efficiencies, then we'd be in a very good position. And of course, I'm teeing up the work we've been doing here in Oxford now, because this is something that I think that will happen, and hopefully it'll happen here in Oxford. What we've discovered is a new family of materials that are we haven't discovered the materials, but we've discovered they're exceptionally good in solar cells. This is meant to be an illustration of a crystal structure. They're called perovskites. They're commonly made with an organic cation, a positively charged ion, a metal that can be lead or tin, and halides. So a typical material would be something called methylammonium lead triiodide. And they work very well as solar cells, very quickly. This is a cross-section of a device. It's a bit simpler than a silicon cell. It's just processed on glass. It's got a conducting oxide at the bottom, the perovskite absorber layer, and then a p-type selective material to make sure the charge flows in this direction. And that makes the solar cell. So we call it a sandwich structure, because it looks a bit like a sandwich. Not very inventive, but there we go. And so very soon we got up to 15% efficiency. And in fact, the efficiency of the best lab-based cells is now over 20% for this stuff. And this is a bit like, it's not quite so impressive as the global solar installation compared to other technologies, but this is now within the solar field. We've got silicon here, and we've got perovskites shooting up here. So again, these guys are starting to look over their backs and recognize that there could be something coming to compete. Hopefully in a couple of years, they'll realize we've done it. So to sort of now look at the manufacturing of this stuff, it's much, much simpler. You start from some precursors, some powders that are the salts. It's not table salt, but it's not too dissimilar and similarly priced. You mix it in a solvent, and that makes your precursor. So this is equivalent to the wafer stage in the silicon cell. And then basically we can coat these layers either by vapor deposition or via solution coating. We need about 5 layers in the stack to make the complete solar cell. So it should be much, much less expensive than silicon. But of course, what's really important is the total power output of the module. Not just because of land area, but there's a lot of the costs associated with deploying PV aren't the module costs. So the existing silicon modules, the cost of the module is less than half the cost of the whole solar installation. So to offset that fixed cost, which is basically determined by the area of the installation, you need to increase the efficiency. So this is where we come. How can we take this stuff and make it much more efficient? Those technologies that are operating above 25%, or above 28%, should I say, are all based on multiple junction solar cells. And to very briefly describe, this is a cartoon illustrating what a multi-junction solar cell looks like. This is a tandem solar cell. We have a top absorber that absorbs only the visible light. So the sunlight is spanning all different energies. The blue light is about 4, in terms of energy, it's 4 electron volts. We can measure the energy of light in terms of voltage. Blue light starts at 4 volts. Infrared light goes down to around 1 volt. And the solar cell can't generate any more voltage than the energy of light it absorbed. That would be disobeying thermodynamics. So if you have a single junction, a silicon cell that absorbs light down to 1 volt, 1 electron volt, you can never generate more than 1 volt from it. So all those photons are collected at 1 volt. If you can split that spectrum up into different energies, you can, for instance, collect the top section at 2 volts, and then you generate more power from that, and the bottom section at the lower voltage. So overall, going to multi-junction increases the efficiency, and the first step is to put perovskite on top of silicon. I'm feeling like I might be getting a little bit technical here, so I'll very briefly scan over this. We can tune the band gap, because what's important is you absorb precisely half the light in the top cell, and the other half that you don't absorb in the top cell is absorbed in the bottom cell. You need to generate the same current from the 2 cells so that you have the best power matching. We can tune the band gap by changing the size of the cation here, or we can change the halide going from iodine to bromine. So it's very flexible in terms of tuning the material. And if we take a material that we tune to be precisely the right band gap to sit on top of silicon, there's some losses here in the silicon, and we stick a perovskite cell on top of a silicon cell, we can take, for instance, a 19-20% efficient silicon cell and bump that up to just a little bit over 25% already with the materials that we're using today. So the indication is this stuff could genuinely deliver 30% efficient wafers over the next few years, and then that could be translated into over 25% efficient modules, which you should compare to the most modules today are between 15 to 17%. So it can be a big step forward. I'm probably going to skip over the next part, but these stuff could also be deployed on buildings, and this is where another area of integration of solar, where instead of thinking it as solar farms, you make use of all the built environment to basically have your power generated everywhere. And the other aspect is to try to integrate it into all sorts of materials, cars, and everything. So power generation, in principle, should become ubiquitous if the technology is right. And one target for cars, automotive, for instance, if you had a 40% efficient solar cell over the whole of the surface of an electric car, you could probably power it without ever having to plug it in, provided you don't park in a multi-story car park. So it works in the countryside. So just finally, on conclusions, PV's already become very, very cheap, and it is cost-effective in many places to generate, not power on demand. That needs to come down further to offset storage costs. The non-module costs are more than 50% of the cost of the PV, which means the most sure way to reduce the overall cost of PV is to have the efficiency increased, and this is being undertaken in the industry through improving silicon, taking the module efficiency from today 15 to 17% up towards 25%. But if we want to go beyond that, we have to introduce new concepts, and this is where the perovskite on silicon comes in, which can ultimately lead to multi-junction, low-cost technology, which should eventually get up towards 40% efficiency. I won't predict when. And the other applications obviously could enable PV to be everywhere. So that's a bit of a biased view towards PV being the only useful source of electricity. Clearly in the UK, wind is extremely important. And the big caveat is we need to scale storage. But what's notable is there's only been one gigafactory. There hasn't been humans have not built a gigafactory for energy storage before. So we can guarantee the cost of that will come down, as all technologies have. And if the first factory is producing batteries at $160 per kilowatt or megawatt hour, then we can assume that's going to keep coming down. And you could imagine $50 per megawatt hour, et cetera, and power will become cheap. So thank you very much.
Great, Henry and Malcolm. I think that was incredibly helpful in helping us understand what the challenges are, where we are, and I'm feeling much more optimistic than I did before this. So we have about, and thanks too for staying so remarkably on time, both of you. We have about 45 minutes to pose questions. Please identify who you'd like to question to go to if you have a view on that. This is being filmed and live webcast, so if you don't want to be filmed and live webcast, it's just you don't say anything. And who'd like to go first? Yeah.
Hello, this is a question for Professor Snaith. I'm David Dent. I've just had about 30 years in the semis industry. This dual technology cell, where you've got perovskite on top of silicon, bearing in mind that the frequency spectrum changes during the day, how closely do you have to match these technologies?
So it's a very good point, and what it means is that so I'll just reiterate your question. As the sun starts from the morning to the midday to the afternoon, the spectrum changes, which means that the amount of light being absorbed in the rear cell and the front cell will be different depending on the time of day, and especially geographic location as well. So the first question is for optimum power average power output over the year. In principle, that band gap of that top cell should be tuned depending on the location. So there isn't necessarily going to be a one-size-fits-all. In terms of how much do you lose if you're comparing a single junction cell of the same efficiency to a tandem junction cell, there have been some calculations done, and I think the value is somewhere between 5 and 10% sort of derating on the tandem versus the single junction. So if the single junction module was 20% efficiency, it wouldn't be worth going to a tandem until you're significantly above 22. So you need to have a big hike.
To Prof. Malcolm, do you think it is possible, you mentioned that it's possible to like connect the grids of the whole Europe. Do you think it is possible for the whole world? And if yes, what are the challenges that we need to tackle?
Okay, so the interesting challenge is so the question is, can you connect the whole world up? So this is an idea that has been promulgated already to say, can we actually do a round-the-world connection, because that gets rid of the solar being dark at night, you can start to do things. In the northern hemisphere, you've got the Bering Straits, so that basically is just a short gap between Russia and the US, so you could go all the way from Spain all the way around that way around, and you can get around to the US, and you can do quite a, probably what's about 2/3 of the way around. Is technically it's possible. The economics of that start to get really challenging, and goodness knows what the politics is going to look like. So the answer is, yes, it's possible, but I doubt it'll happen in my lifetime.
Is it worth it?
Okay, so is it worth it? Well, the challenge is, okay, so what's really interesting is that you're trading off storage versus transmission. And the question that you're going to have to ask is to say, how fast are the costs of storage going to come down compared to those transmission costs? And so my instinct is that, and I've got no figures to back it up, just my instinct is saying the storage is coming down faster than the transmission will actually cover.
Damien Culshaw, I'm a wind farm developer, but don't hold that against me in this audience. Question for Malcolm. You gave a very good indication of the scale that we need to achieve if we're going to manage the balance between supply and demand using storage, but you didn't really touch on load management. Would you like to comment on the scale of the challenge if we're going to do a significant amount of balance by load management?
Yeah. So the question is to say, what's the role of load management or demand-side management? How do you manage that? The challenge comes into saying, at what point are you prepared to compromise delivery of service? And if you're not prepared to compromise delivery of service, in other words, if I told you you cannot have a meal between 5 and 9 p.m. in the evening, how happy will you be? Or put another way, what incentive do I have to give you in order not to do that? And what I find is that in actually to get people to change that level of behavior is extremely challenging, even in industrial contexts. However, I think there's a slight loop around that, and that is to say that if you can store service so that you can still provide that service even though you're not consuming energy, then I think there's a lot more opportunities to do this. A simple example is, for instance, if I said that you cannot use hot water between 4 and 9 in the evening, you wouldn't be very happy. But if you said, okay, if you've got a hot water tank, you can use it as much as you like. Your hot water tank can't actually go on between that and that time period. Then you can start to really start to use that. And just to give you an idea, there is something like 40 gigawatt hours of energy storage in hot water tanks in the UK at the moment, which is 4 times the largest pump storage scheme to Norway that we have got in the UK. So there's a huge amount of potential there. The question is, how do we leverage it? What are the markets we put into place so that we can actually bring that into play? Capacity market is starting to get there, but I think there are better opportunities, and that's one of the things we want to explore, is to say, what are the market developments required to leverage that huge amount of storage and service that allows us to have that flexible demand usage. Okay.
You might not want to not cook, but you might not mind if your deep freeze goes off for an hour or something. Or your clothes washer or something else. right? So, I mean, it's also optimizing on the house.
Yeah, the thing is that if you have a look, your big energy users are is space heating and hot water heating. Those are your big energy guys. Those are relatively easy to change. Refrigerators, they're becoming far more efficient, so actually the amount of energy that's stored in there is getting smaller and smaller as time goes on. We found, to my cost, is that people struggle with emptying the washing machine or the clothes washer in the mornings because they've got different time schedules. It's a question of how do you get the human behavior to work correctly with the system.
Okay. Woman over there.
My question is for both of the speakers. At this stage, how much conventional energy do we need to produce energy from renewables, and how efficient is it? So how much energy do you need to put in to produce energy from wind turbines or solar cells? And how long would it take for us to replace conventional energy with solar energy? Or
I can do the PV side. I mean, the silicon PV that's being deployed has got about a 1.5-year energy payback in sort of mid-Europe, and it's less as you go further south, can be down to less than a year energy payback. That's in terms of the amount of actual energy you have to put into making the stuff versus the electrical power it puts out. So it's a relatively short time. So, you know, within a short period, you could, you'll be getting positive payback. I haven't done the calculation as to if you wanted to, within a 5-year period, produce, you know, 18 terawatts of electrical energy by PV, how long would you have to be putting energy in before you start to get energy out? But presumably it'd be on the order of a year, depending on your ramp rate.
Yeah, wind's about the same. It's slightly less. It's probably between 6 months and 18 months, depending on the wind conditions, your energy payback time. And these guys last for 25 years, so it's pretty good.
I've heard the statistics. It doesn't do us any favor, but if you compare it to coal, I think a coal power station is about, it's 6 days or something like that. So that is all about the resource you're putting in rather than the infrastructure you put on. Yeah.
Gentlemen.
Hi, Tony Bowie from Ensham Green Tea. On that theme, what are the economics of wave and tidal power? Obviously, they're geographically specific to continents, islands, channels. And what about the scaling of that? Because that would seem to be a scale and payback problem. And has similar work been done on forecasting reductions in cost and increases in efficiencies as you've done with solar and other sources?
So I'm not a civils person, but I work with the civils people in this. And tidal is, you've got to be very, it's very geographically limited. So you got places like our west coast, and you've got Bay of Fundy in Canada and parts of China and places like New Zealand through the straits there, where tidal is really good. And there you're looking at levelized cost of energy equivalent to nuclear. So it's that kind of level. And so, but the total resource that's available globally is quite small. Wave is a lot more challenging. If you look at medium depths, so beyond 20 meters of depth of sea and beyond, I don't think many devices survive more than a year. So that's still technology which is still to be proven. Even Polaris, which is the one that was doing the best, only lasted 9 months. So it's challenging.
We had in the school a tidal power generation research group. In fact, you'll still see some material on our website. And some of the insights on that is just to reinforce what Malcolm's saying. Very powerful in isolated locations. A big issue is the materials don't withstand the pressures. And salt is just incredibly corrosive even for all known steel. So I've been, most of these tidal power plants don't work for most of the time. The other sort of opportunity is sort of a 7 estuary. That's not really, that's really hydro storage, which is where there is rail potential.
Yeah.
Personally.
Hi, my name is Mohammed Zia. I'm a postgraduate in public policy. On the map that you showed of different parts of the world that have the highest exposure to sunlight, a lot of those places were in Sub-Saharan Africa, the Middle East, South Asia. I have a two-part question. One is, do you know of particular governments, international organizations, private sector companies that are trying to exploit that potential? And could you talk a little bit more on the financial kind of mechanics of doing that? You know, on the user end, is it financially sustainable? Is it financially sustainable from the business end, et cetera?
Okay. I'll maybe start on that in terms of the solar energy is deployed where you need to use the power. So there's solar deployed all over the world, but it's where the power's demanded. There aren't the transmission facilities to sort of fill the Gobi Desert or Sahara Desert with PV and then just power the rest of Europe. So the cost of putting that massive infrastructure in is not there, so that is not really seen as a economically feasible route. But certainly deploying PV in locations of higher solar irradiance where there is a power demand is less expensive than like in the UK. So there's more PV deployed in those places. But there's what you really want to do is deploy it where you need to use it, because then you don't have the additional costs of the transmission and the grid costs. But there's a whole other sort of equation of obviously where are you using your power, what time do you need it, and it comes back to the storage issue of the fact that you need to also produce the power on demand, and it's not generated on demand.
What about like mega cities, or like Cairo, for example, where there is huge demand, or cities in India?
As far as I'm aware, no one's specifically exploiting that to produce power for those cities. Their conventional power economically is probably produced relatively inexpensively through, I'm not sure on the specific issue, but through coal. So it's still not cost competitive. As soon as it is, then it becomes an economic.
Okay, let's go to the back towards the back of the room. Any hands up there? No? No?
Yeah.
So on one of the graphs, we saw a big increase in the installation of PV in the UK. But what do you think the effects of the upcoming cuts in subsidies will be for the continuing installation? And do you think it'll ever be possible to install PV in the UK without a big subsidy?
So if I answer the last question, it absolutely should be possible to install it without any subsidy. And clearly the way the technology is going, if it reduces in cost by another 100%, 50%, so halves in cost, then it'll be the same cost in the UK as it is today in southern Spain. So in principle, in a short while, it should be cost competitive. There are, I'm aware of, a lot of people stopping solar installation with the new changes in subsidies. So it will have an impact. We'll probably see a plateau for a while or a slower increase, and then it'll pick up again as the technology gets, again, economically more viable. It's a shame the subsidies got pulled as they have been quite so abruptly and now and not in a year or 18 months' time, when the cost would have come down to make that more manageable, I think, for the UK. So I'm sure that will have an impact. This curve, specifically in the UK, is not going to keep going at that same rate over the next couple of years, I don't think. I don't know if you might disagree with that.
No, I was going to say exactly the same thing. The only thing that it might do is that, remember Henry said that the balance of the cost is beyond the module is quite expensive, and a lot of that is about installation. So what it might actually do is those people who can drive those installation costs right down could probably still succeed. So there's a slight glimmer that it might really drive innovation in this area, but who knows? Otherwise, exactly the same as Henry. Yeah.
I want to go to this guy. Go back.
Right,
sorry, it was the person next to you.
So this is for Professor Snaith. So as far as I'm aware, one of the big problems with perovskites is their degradation because of moisture. How are you overcoming this, and can you really see a perovskite cell being stable over a period of years?
Yeah, I mean, the materials as made, and certainly the first materials that we've made, are sensitive to moisture because one of the components, the methylammonium iodide, is soluble in water. So sounds like a killer. I'll try to explain to you that it's not. It's not game over yet. So they certainly, if you put the unprotected film in a humid environment, it will decompose back to lead iodide, which is one of the starting components. So one of the things we're doing that we've managed to do to overcome this is looking at different cations, stuff that's less soluble in water, less sensitive to moisture, treating the films so that they become actually hydrophobic in themselves. And then the solar cell, the perovskite, is one layer in the device. It's then contacted with different materials that are the P and N-type materials, and then you've got the electrode materials on the outside. So all these materials that sandwich the perovskite, one of their properties is to protect that from the environment. And then after that, we laminate it between two sheets of glass with protective barrier layers. So actually we have data for devices that have been for thousands of hours at 85 degrees with 85% humidity, and the cells aren't degrading, and also under full sunlight at the same temperature with UV component, and also even in the dark. And one of the things we're doing is also trying to stress these cells unencapsulated in air at 85 degrees just to see what happens. How good can we make the whole transporter and the protective electrode layers? So in essence, the material itself, you don't want to stick out in the sunlight on a humid day, it's not going to last, but you sandwich them between different layers, we tune the materials. Basically, there's a fair amount of chemistry and just materials development and material science, which is making them very robust, and I'm expecting them to be as good. They should not be limiting the device stability.
Doesn't that massively bring up the cost in terms of producing it?
No, the sort of encapsulants that we're using are exactly what's used in the silicon industry. So silicon PV cells are actually making the move. The cheapest ones use a polymer backsheet with a glass front encapsulant, and they're going to glass laminates because they get longer lifetime. So it's completely in line with the most efficient, longest lifetime PV deployed already.
Did you have a question? Oh, well, there you go. John?
What's the scope for retrofitting perovskite panels to existing solar installations?
So in principle, what I described, well, one of the things been described is what we call a two-terminal device, where you deposit the solar cell directly on top of the silicon cell, and it just looks like a wafer. But the alternative is you make a separate perovskite module and then put that in front of a silicon module. In reality, if you're making one module, you wouldn't make two separate modules. You put the cells on top of each other and laminate it. So there is a prospect of taking a perovskite semi-transparent module and just bolting them onto the top of existing silicon PV. But I think in reality, you then have to put in an extra power network, the whole of the balance of systems you'd require from the perovskite module. It feels to me like it's going to be more cost effective and better to put a whole new module in, but it's something we haven't fully calculated, and it's feasible that you could have a gain there. If you were going to try to develop, you could compete it, for instance, against just putting perovskite out as a single junction technology on its own to compete. And if we can integrate that on top of existing silicon, it's feasible. My feeling is the frames won't be strong enough. You put in a whole extra module on, you're going to have to put in all the new power handling for the perovskite side. I don't think we'll be able to sort of piggyback in and sort of bypass into the silicon cables, but I might be wrong there. So it's something we have considered it. My gut feeling is it's not going to be practical, but it would be nice if it could be done.
Okay. Why don't we start here, so you here, and then I will get to the back again.
You showed the solar and wind power station. I was wondering where that's being built, and also if that's the optimal generation idea, or if it would be better to maybe save land use and put it on.
Sorry, which that, are you talking about the battery manufacturing plant, or is that the very last picture that I had?
Yeah.
Okay, so that's a battery plant,
Okay.
and it's got a lot of solar and PV there because a lot of energy goes into making batteries, and that's in, just gone out of my mind, it's in the US, and Nevada, that's it, thank you. It's in Nevada in the US. And actually there's an interesting, if you go and have a look, you can find an article, I think it's in the Inquirer, about what Elon Musk's strategy was in finding that right place to put it.
Well, then my question, I suppose, is separate to that. Do you envisage these solar cells like as solar farms, or to save land, just putting them on sort of everyone's roofs?
So working on everybody's roofs doesn't make sense. It makes sense to put them on the right side of roofs. I think that's the right place to start off with. The problem is your installation costs are high, whereas if you put them on the land, they're much easier to install and deploy. The challenge there is if you start to do too much of it, you then start to compromise the agricultural business of that. There's a balance to be played there. One of the piece of work that I've done in the past is looking to say, if you did a sparse array, in other words, you don't put them side by side, but you actually spread them out, you can actually get it so the light conditions still allow for grass to grow underneath, and you can still do grazing underneath. Remember, we said 60% of agricultural land is grazing. So there's potential to work with grazing land and solar.
Yeah, no, I'd just say there's for sort of generically termed building integrated PV, so not going for what you're putting on the roof, which is termed building applied. That is currently about 4 times as expensive to install as the solar farms. But if you can design new buildings, or a lot of buildings also need to have new skins put on them because they're not energy efficient, so they need to be reclad. So there's a big opportunity there for retrofitting buildings. If you can have your PV material into the cladding, and modern buildings are built with something called curtain walls, which are basically factory built 3 by 1.5 meter or 3 by 1 meter, 3 by 3 meter sections that just get hung on a frame. So the PV could all be put into that curtain wall, and then it's hung in. And if all the balance of systems is included in that, then in principle that could be integrated for relatively little additional cost compared to the cost of building the building in the first place. So that's a way that people are considering integrating PV more effectively into buildings. And with that comes a whole other section of what do you do with the power that's generated in the building. And I mean, for instance, with your computers, you probably all plug these in with your transformer into your 240 volt socket, generate a lot of heat on your desk in your transformer, and then transform it back down to 12 volts or 9 volts. So the notion is that all buildings should have a DC circuit that's at sort of 12 or 9 volts, and then you don't have the inversion cost, so that's an efficiency gain, and you don't have all this transforming and retransforming back from AC to DC, which you lose about half your power. So in principle, you could power all your electrical appliances and all your LED lighting from the building. So that would be a big saving. And that's something, but it's going to be slow because there's a whole construction industry that needs to get behind it.
Are you also doing translucent glass? Just have your windows being your power generators?
That's something that's certainly a prospect. Our sort of investigations, there's a lot of enthusiasm amongst architects, especially for trying to have new technologies that mean you can just glaze your building. Your whole building can be PV, whether it's the vision glass you're looking through or the more opaque part of the glass. But the practical sort of limitations of the construction industry basically are slowing down the integration of this. And of course, at the moment, there's not really a really good technology that can fulfill that. And the additional cost of the PV has to be offset as well by the amount of power it generates. So it has to come in economically also.
All right, we'll go to the back and take that hand that's been up for a while.
Hey, just a quick question about access to capital markets. So you showed this huge kind of rise in installations and everything. And you know, from my previous work, we did a lot of installation projects in Southern Africa. And some of the problems that we had was that we needed to get banks comfortable with lending in these structures. So with these big scale-ups, where are the credit and capital markets for them? And is that going to be a bit of a hamper coming up as well?
The short answer is yes, it's going to be a real challenge because that's a lot of money to be raising. The slightly more nuanced answer is that I think, as Henry was mentioning, actually the risk for conventional power systems is even going to be higher. And so there's going to become a breakpoint where the value is going to be so large because of that dearth of new generation coming through that those capital markets will see the value there and take that additional risk and take it on. I think it's going to be, you know, it's no mistake that both China and the US were the biggest kickers against climate change, because what they were doing is basically building up their technical and economic capacity to deploy this big time, and they were getting a running head start. And you can start to see that both of those economies are being able to access the large capital markets to do those massive deployments.
Anyone back there? No.
If you're setting up a solar array in the country, does it make more sense to lie the panels flat, passively on the ground, or make them dynamic so they track the sun?
It certainly makes more sense in terms of the amount of power you're going to get out per square meter to have them tracking the sun. Up until now, it's been more economically viable to have them in fixed orientation. And if you want to maximize for any single array the total amount of power output, they're generally facing south. Now, in the northern hemisphere. Now, if you want to actually maximize the useful amount of power produced from an array as the amount of deployed PV goes up, then it could make more sense to have them actually east-west facing if they're fixed. But as the efficiency of the modules go up, the cost of the single-axis tracker, so not stuff that points directly at the sun, but stuff that might move around on a single axis, the cost of those systems is coming down as well. And at some point, it'll be more beneficial to use single-axis tracking with, say, the module efficiency of 30% than it is having flat plate, because as your efficiency goes up, you're producing more power per tracker, and hence it's offsetting more and more of that balance of systems cost. So I'd predict what we'll see is a move towards single-axis trackers, and then with the increasing in efficiency of the modules as well. And that will also help us balance the power output. Another thing, in terms of the sort of license to put in a PV farm, it's usually warranted in terms of its peak power output. So if you now have a fixed bit of land and the PV installation is actually cheap, you could envisage that you limit that peak output so you can actually get your time integrated output for any given peak being maximized. And you could do that again with single axis trackers, because you wouldn't necessarily have them all pointing at the sun in midday, because you want to keep a flatter spectrum. And that'd be a way of offsetting storage. If the cost of PV is deployed and keeps coming down and down, in essence you offset your storage by spreading your load profile or your generation profile from the PV array. A bit more than
okay, let's see the show of all the hands of anyone that wants to ask any more questions. Just the two at the back, or four at the back, and then we'll stop.
Yeah, I just had a quick question on, is there an example of the building that you talked about that somebody's trying to build that has the full array of kind of solar, like walls and solar outward-facing arrays?
Yeah, there are some examples, especially with crystalline silicon. So the way people make sort of semi-transparent modules with silicon is you just space the wafers out. So little 4 or 6 inch wafers, and they're basically laminated between sheets of glass with space in them. If you want to see some, I believe in King's Cross train station, there's a bit of a roof that's got some sort of semi-transparent perovskite cells. There are quite a few buildings that are more than King's Cross tube station. There's some in Germany where they've got the whole building is made out of this stuff, and they're, if I can remember correctly, you're talking about sort of 1 megawatt buildings under peak load or something like that. I might be wrong there though on that value. So they are, but they're very much sort of early adopters, sort of trying to demonstrate a concept rather than something that's been deployed widespread, let's say.
This is a quick question on the storage challenge that you alluded to. So what is the most promising large-scale solution to sort of having significant energy storage capacity? Is it batteries or pumped storage?
So the interesting question is remember we talked about those learning rates, which is basically saying that if you double the amount of installed capacity, that then drives the cost down. The only technology which is having a really fast push down that track is lithium-ion. Because you've got mobile phone technology pushing that, you've got PCs pushing that, you've now got electric vehicles pushing that. So what we're seeing is that's the one that's kind of winning that race. It's very much like silicon. I mean, you saw silicon's not necessarily the best one there, but the learning rates that have been put into that are massive because the large labs come through. What I think the kind of interesting one that I think is going to start coming through are flow batteries, where you can start to have the large energies with a smaller power handling unit. And I think that's the one that's going to come through. There are other things. The other one is it's kind of like a semi-storage technology, which is thermal. So thermal storage is a lot cheaper and a lot easier to do, but doesn't necessarily give you the high-grade electricity coming back. That's a quick answer. Hydro's we've kind of saturated the hydro in the world. There's probably about another 20% to go on hydro, and that's it.
There's some more hands back there.
Are there any natural resources that will be put under significant pressure by scaling up renewables or implementing storage? So metals, like metal limitation.
So something you might have heard about is indium, the transparent conducting oxide on lots of solar cells is indium tin oxide, and indium is relatively scarce. It's mined as a byproduct. I think of aluminium mining, it might be zinc, I always get confused. Tellurium's the other one, but that is used in our touch screens. So actually a lot of the production is already used for screens. We've got a lot of screens that use ITO. So in principle, you could say that's a scarcity that might be problematic, but there's lots of people working on alternatives, zinc oxide, aluminium doped zinc oxide, and they're completely abundant. So I don't think there's any real scarce elements in silicon or in the perovskite stuff we're doing at least that is going to pose a real problem to scaling and then depletion of natural resources. One good thing about lead that we use is it's very abundant.
So the other one in batteries is of course the big one is lithium. And there's probably enough lithium resources to see us through the next 10 years or so. And there are quite a lot of alternative battery technologies that will come through and replace that. But that's probably the one that I'd worry about the most.
Final question.
Yeah, one for Henry. So you touched in answer to one of your questions about going more high-tech in terms of the mounts for solar farms with rotating axes. Is there also the potential to go more low-tech and get rid of all that steel we use to support panels and just lay them out in a plastic film in somewhere cheap like a desert?
Yeah, I mean, there's a lot of people working on trying to work on what are fundamentally very inexpensive solar cells on metal foil. Like we can make this stuff on aluminium foil. There's other technologies, some of these thin film technologies can be made on metal foils. One sort of technical challenge is the stuff still needs to last for long enough that it's worth making and deploying, and the protective barrier layers to keep the moisture out, even for any PV technology, to keep the oxygen out, are generally quite expensive. Now, there's a lot of, if they're not glass. Glass is the cheapest, best barrier currently that we know. Now, there's a lot of motivation to finding better barriers and good barriers, and there's a lot of people working on it. So it will happen. Now, the question is that deployed, cheap, rolled out PV has to not get covered by a sandstorm. It has to not be blown away. It has to actually be there. And at the end of the day, you do want something quite rigid, or at least very well pegged to the ground, that it's going to last for long enough to produce the power. And you still have to have all the power handling, the inverters, the cables, the electric. So I don't know if there's a sort of notion that if you could make a solar cell that's 5 cents per watt peak and just roll it out, you can produce all the power you need. I'm sure there'll be a big market for that sort of PV. But I don't think it's needed. It's clearly not needed to get to the sort of scale. You know, glass-based rigid modules can produce all our electricity if we want to make them, if we have the resources to make them. But it's something that I think will develop alongside. My bet would be that rigid PV will always last for longer, and you'd prefer to put an installation that lasts 50 years than a lightweight one that you've got to replace every 10 years or something. So, but there'll be a market for it. Yes, that's it.
Thanks very, very much. Just before we thank Henry and Malcolm for, I think, what's been a really incredibly insightful and very, very well-timed as well in terms of your introductions, series of presentations, but also responses to very good questions. Let me just highlight some of the forthcoming events, and if you've learned so as much as I have from today, I'm sure you'll want to come back for some of the others. Next Thursday, in the same seminar series, we have Nick Bostrom, who's the director of the Oxford Martin School's Future of Humanity Institute, That event is actually full. So if you do want to come and you haven't registered, I think the best thing to do will be to stay at home and watch it on the webcast. The following week we have Brian Nolan and John Mulbauer, who's sitting here, talking about inequality and its impacts. The seminar is called Mind the Gap, obviously an absolutely key dimension of a global challenge. The following week, that's 12th of November, Angela McLean, who's the director of our Institute for Emerging Infections, on understanding the threat of emerging infections. We also have two special events I want to draw your attention to. The first is on Wednesday, the 28th of October, at lunchtime at 12 o'clock. We have David Black, who's the MD of Google, talking about the internet and innovation. And then on the 23rd of November, we have our Sheldonian lecture at the Sheldonian Theatre, our 10th anniversary celebration by Lord Rees, the Astronomer Royal and Professor of Cosmology at Cambridge. And Martin will speak about world technology's dark side, eclipse humanity's bright future. So the future of technology and its impact on society. And for those of you that don't know Martin, well, maybe it's a risky thing to say, but I think he's the smartest person in Britain. So definitely worth hearing, and certainly someone who's thought deeply about the future of humanity and our planet. Thanks to you all for coming, and thanks particularly to our two great presenters today. All power to you, if I may say, without too much of a pun, and good evening to you all. Thank you.